Hello, good afternoon. Today, right, we'll go through WEP, do a conceptual review. In this entire review, right, there wouldn't be too much of examples, so apologize for that. It'll be more concepts. I plan for this review also because later on, right, going into gravitation, you actually need a lot of these base concepts from WEP to enable you to understand what's going on, okay, in gravitation. So without some of these basic building block, right, I believe when you go into gravitational potential energy, you will struggle, and you will not appreciate, right, why the definition of gravitational potential energy is constructed as such. Yeah. So without further ado, let's begin. First up, right, we are going to revise, right, what is meant by work. Okay. Work done by the force, right, is the product of the magnitude of the force and displacement in direction of the force. Yeah. So this, right, tells us that only a particular component of the displacement is relevant if, right, the force and the displacement are not collinear. For example, in this diagram, right, you can see that the force is at an angle to the displacement. So here, right, you would have to consider what is the component of the displacement, right, in direction of the force. Or vice versa, you can consider the component of the force in the direction of the displacement. That's fine as well. They'll give you the same thing. So in the way, right, this diagram is structured, the work will be equals to Fs cosine theta. Yeah, it doesn't matter the cosine follow the F or the cosine follow the S, because when you multiply together, it will give you the same thing. I don't want to put any formula here, right, that involve the theta, because, right, sometimes the context may be different and you have to figure out, right, which is the relevant angle. Okay, so I don't want to put a cosine theta in the formula. I'll just keep it general and just say, right, this work is equals to force times the parallel S. Okay, yeah, that will be good enough. You will figure out, right, what is that in the context of the question. And once we have this formulation, right, we can ask ourselves, what if, right, we consider the time derivative of this formula. So in other words, trying to find out what is the rate at which work is done. Okay, and that is nothing other than power. So if you derive the if you differentiate the right hand side, okay, and you take F as a constant force, in reality, right, it doesn't have to be, but in this formulation, right, I don't want to go into the detailed calculus, right. So the simple way is to just look at F as a constant force, and you can have the S over dt to give you V. Okay, so that's where, right, the P equals to FV formula come about. I believe in many lecture notes, right, work done is introduced like the first thing in the WEP lecture notes, and power equals to FV, right, is like introduced as one of the last things, because they are following the syllabus. And you may feel, right, that these two things are very detached, but actually, right, they follow with each other, right, so well. Okay, they are one and the same thing. And here, right, I just have a few questions, right, for you to ponder. What if, right, the displacement is in the opposite direction? What will happen to the work? So I have given the answers here. So work done will be negative. Next question is, does negative means that the work is in opposite direction? Answer is no. Work and energy are all scalar quantities. Scalar quantities, right, they have no property which is called direction. Yeah, to them, right, the number is simply a value on the number line. Okay, the negative value, right, simply means that it is lying on the left hand side of 0. That's all. It's just a relative value. Oh, it doesn't mean direction at all. But you'll still be a bit unpersuaded in this, right, because you feel that the force and displacement are both like vectors, right? Or how do they give rise to a scalar? Yeah. To answer this question, right, you just need to go to your math vectors topic. Look up this thing called scalar product, also known as dot product. It is a scenario, right, whereby two vectors multiply each other to give you a number. So what's the significance of a dot product, right? It is actually taking the shadow of one vector in the direction of the other, or taking the length of the shadow. So a length of a shadow, right, has no direction per se. It's just a length. Yeah. What if displacement is perpendicular to the force? Then you have zero work. Okay. The most prominent example will be centripetal force. Although we know centripetal force is a net force, it's not a real force, but what we are referring to in this phrasing is saying that there is no net work done by forces in the radial direction that constitute the centripetal force. Okay, so these are just some snippets. Okay, Q&A for work. So now let's go on, right, to this idea called potential energy. Potential energy, right, is a very peculiar thing. From Sec 3, I believe, when you do secondary school physics, right, you're already very familiar with potential energy. And there is a very easy formula for GPE, which is just mgh. And you think you have understood it very, very well, okay? But right, do we really understand the nature of potential energy well? So let's just suppose, right, we throw a ball up in the air. So at the beginning, right, the ball will have the greatest KE. KE disappears as it goes upwards and reappears, right, as it comes down. So come down. How do we know? I mean, K is half mv squared, okay? So the speed, right, decreases on the way up, increases on the way down. So KE also follow the speed in this manner. Then, right, where did the KE go to as it goes up? And where did the KE come from as it comes down? Okay. To understand why, right, there is a need for this PE, but this concept called potential energy, right, we really need to ask, right, where did the KE go to? So we actually, right, go into something we call, and it's just an imagined account, or you go to an account called potential energy. And K is sort of like real because, right, you measure the mass, you measure the speed, or you come out with a formula half mv squared. It's very real. At all points, right, you can measure the mass again, measure the speed again, and you know the new KE. But how do you know what is the potential energy? You can't really, right, measure it per se. Okay, we imagine it, and we come out with a model like mgh to describe, right, the value. But intrinsic to the object, right, it is a KE. Okay, so this sort of, right, the way that people were thinking about this, right, when they were first coming out with the idea of PE. So they were thinking PE is like an invisible yet very reliable bank. Okay, invisible because, right, it can't be seen. Okay, reliable because, right, you put in how much, later on you can withdraw how much. Yeah, it doesn't cheat away your money. So, and this bank, right, deal with not money but kinetic energy. Yeah. So that is really, right, the idea behind it. So now, right, if we were to ask ourselves the same question, where did the KE go to? So the KE, right, is like deposited into an invisible bank called potential energy. Okay. And when the time are right, the bank will return you back the KE. At the right position, it return back you the KE again. Or you can think in terms of gravitational potential energy, elastic potential energy. The speed, right, for the object, right, depends on, sorry, the KE of the object depends on the position. So different positions, right, you will have a sort of a predetermined potential energy and a kinetic energy already. Okay, and it goes between these two accounts. Here, a question to ask, right, is I don't know whether this question sounds weird to you or not. Okay, who runs this invisible bank called PE? The answer is, right, something called conservative forces. Okay, conservative forces, right, are the type of forces that are qualified to run PE banks. Okay, other non-conservative forces, right, not qualified. It's just like not everyone can open a bank, okay, as and when you please. Only certain people qualify to open. So in this case, right, is forces like gravitational potential, gravitational force, electric force, elastic spring force. Yeah. So these are like the bankers who are given the license to run this bank. Forces, right, like friction, cannot, because right, they will run away with your money. Yeah. You deposit energy with friction, right? Then friction will run away. You wouldn't be qualified to run a bank. Obviously, it won't return you back. So that's why there's no something like called frictional potential energy. No such thing. Yeah. And where did it squander your money to? It squander it, right, in all ways. Okay, like in the case of friction, the Ke, right, converted into thermal energy of the surface because the surface warm up, right, as the rubbing takes place. Yeah, so it's just like the banker, right, squander away the money, go and gamble, buy iPhone, this and that. Okay, or took your money and never plan to return you back. Okay, now, right, let's think about this analogy of a wallet plus bank account. Okay, suppose, right, you have $1,000 in your wallet. Okay, anytime, right, you wish to go to the bank, put in some money, maybe you put in $500, then you realize, right, that your wallet will have less. Okay, where do you go to? It's in the bank. We understood this so far. Anytime, right, you count your wallet, right, if you left with $200 in your wallet, then you recall, oh yeah, actually yesterday, right, I deposited another $300 into the bank. That's why from 500 I'm now left with 200. Or anytime you look at your wallet have 900, then you recall, hey, how come got more money now? It's because, oh, yesterday, right, I withdraw more money out. Yeah. And at all times, right, if you count the money in a bank plus wallet, right, they will always give you the same 1,000. Yeah, because, right, you have done nothing to spend it. Okay, you have done nothing to earn more. So if nobody disturb your wealth, yeah, your total wealth, right, like people eye your money, want to borrow from you or what, right, or you never want to spend, then you will always have the same amount. And what are we referring to here? We're actually, right, taking an analogy to Ke and Pe. If nobody disturb the system, okay, which is just the collection, right, of the relevant things we want to study, then the Ke and Pe will just be a constant. Okay, and if you want to change this total amount, then you have to do something. For example, I want to buy chicken rice, or I buy chicken rice, so I'll be $5 poorer, so I'll have only 995. But then, right, after I eat chicken rice, right, I feel, oh, I'm ready to do work, so I go and help my mom sweep the floor. My mom give me $10. Yeah, so you see, that is, right, ways that you can grow your total wealth. In the same way, right, how can you grow your total energy? Okay, or how can you change your total energy? You must do work. Okay, and there are different ways to do work. You can spend money, you can earn money, you can do positive work, you can do negative work. Yeah. So essentially, right, work is the thing that causes total energy to change. Okay, and what work? External work. Yeah, external work. Work done by external forces. And in a system, right, often there could be more than one force acting on it. Some of them are helpful. Okay, they push the system along in a way, right, that causes total energy to increase. Some forces could be acting in a not helpful way, or they oppose your motion. They cause your energy to decrease. Okay, so if we were to write this same thing, right, in an equation, this same thing, right, will appear as such. Net external work will be equals to change in total energy. Okay. Total energy, right, you can break it down further. Since we know, right, it doesn't matter how I call my wealth, okay, because it's my wealth is either in my wallet or in my bank. So if, right, I have done a network, right, then I need to account this network by the change in my wallet plus the change in my bank, because I could have, right, spend $3 or $5, right, from my wallet to buy chicken rice. Yet, right, my mom deposit the $10 into my bank account. Yeah. So if I just look at my wallet, right, I couldn't get a good picture of whether my wealth increased or not. I need to look at both. What's the change in my bank account and change in my wallet to understand the net effect of all that I have done. Okay. And if you understood whatever I said thus far, right, it's very good already. Although I'm using analogy, right, and not talking about equations so much, but that understanding is actually more important. All the equation and the mathematics, right, are actually trivial, and they are only difficult, right, when you don't understand the concept behind them. Okay, so spend time, right, always to understand the concept behind the math. Then you realize the math works out to be just fine. Sorry. So now, right, let's dive in a bit deeper into the relationship between work and potential energy. And we'll study, right, this relationship, right, through graphs. So let's first look at a simple graph, okay, whereby, right, we have the force, right, vary linearly with x. This is not even simple anymore per se, because, right, whenever people quote the formula for work, they simply say that W equals to Fx, which is this formula. Yeah. But they got to realize that if the force is not constant, that formula is actually not applicable. Okay. So you actually, right, need to consider what is the work, right, done by the force in segments. Actually, I have it better here. Okay, I have it better here. So let's consider this diagram instead. So you see the force, right, is almost constant if you consider segments of displacement, right, which are so tiny. Okay, because as you move that small little distance, right, the force overall is non-constant, but during that short instance, right, is almost constant. So what is the work? You'll be the force, which is a constant value, times the small displacement, and that's a small work. If you want to find the total work, you have to sum it all up, okay, across all the strips here. And summing up, right, in this manner is called integration. Yeah. Graphically, it is area under the graph. In other words, right, to find the work done by a force, it is always looking at the area under Fx graph. Oh, that is the generic interpretation. I repeat, so the work done by any force is the area under the Fx graph. Could the graph be negative? Could the value of F be negative? Certainly yes, because, right, the displacement direction, right, as the positive x-axis imply, right, you're taking displacement as the reference. So if the force, right, happens to be opposite to the displacement direction, then the force on this graph, right, will appear in the negative zone. Yeah. So you will have end up negative area under the graph, which makes sense because, right, that will lead to a negative work. Coming back to this spring force scenario, if you want to find what is the work done by the spring force, is simply area under the graph. So it will be half Fx, where F, right, is any point on this graph. Yeah, any point on this graph. And F in turns is equals to Kx. So the work done in stretching the spring, right, is equals to half kx squared. Okay. This one, right, students struggle, unfortunately, because, right, they rely on this formula to understand, to figure out what is the work done. They didn't realize, right, that it's actually area. So they always, right, work done by spring force or against spring force equals to force times distance or force times extension. So in doing so, you miss out a half. Yeah. So correct understanding is always area under graph. Okay, with this, right, I will dive deep into the next part of the same thing, okay, which is, right, to understand a bit further how work relate to the potential energy. And in this example, right, I will use gravitational potential energy, okay. I could have used other things, but unfortunately, this is in the syllabus, so I'm just covering it, right, to be complete. Suppose, right, we have an object, okay, so you follow my mouse cursor. It's being moved, right, away from Earth. Yeah, it's being moved away from Earth. And we don't actually want to incur any change in speed, okay, because we want to keep KE constant. We want to see, right, what is the effect of work on potential energy alone, okay, because we know that work, right, can change the total energy, okay, and total energy is made up of both KE and PE. So here, right, I'm saying, right, let's not touch the bank account. Oh, sorry, and let's not touch the wallet. Okay, let's keep the wallet constant. So I'm saying, right, I'm now going to do work. Okay, and I'm going to distribute newspaper. Okay, and work at a restaurant, whatever. Okay, I want to see how my wealth, right, grow, and I want to track it, right, in a way that is easy, or just look at the bank account. I don't want to count my wallet and the bank account because that will complicate things. Yeah, because my employer always pay me in my bank account. So to do that, right, someone needs to apply an external force because, right, we know gravitational force is attractive in nature. So in order you want to move something away, right, you need to lift it up. Yeah. In order not to speed the thing up, right, you just want to apply an external force that is equal to the weight at every point in space. Yeah. So you don't have to do extra. Just nice can already. So in doing so, right, you see that two forces are always equal and opposite. Yeah. The external force is outwards, weight is inwards. On the fx graph, you see external force is positive because it is in a positive displacement direction. Yeah. Whereas fg is negative because it is opposite to where you're moving. So we actually don't need to know the math. I'm just drawing this graph, right, for you to see that they are opposite. Okay. And hence, right, if you want to know what's the work done by the external force, you will figure out what's the area under the blue graph. Yeah. And work done by gravitational force will be area under the red graph, which is same in magnitude, right, as the blue area, except, right, it's negative. Yeah. So now, right, let's follow this logic chain. As the object goes away from Earth, work done by external force is positive. Yeah. So the first line, we just mentioned it. We also know, right, through our knowledge thus far, okay, potential energy always increase with distance. Yeah, for gravity. As you go higher, GPE increases. It doesn't matter whether you go 1 meter higher or in this case, right, into outer space. Yeah, GPE still increase. Now, let this, and the third point here, right, is what I said just now. The blue area will be equals to the negative of the red area. With these 3 points together, right, now, how can we say, right, what is the change in the GPE? Okay, the change in GPE, right, will be equals to the net external, sorry, is equals to the work done by the external force. Okay, yeah, which is also hence equals to negative of the work done by gravitational force. Let me repeat myself one more time. You see, earlier, right, we have talked about how net external force will change total energy, right? And in this case, only got GPE that's changing. Therefore, the change in GPE, right, will be equals to the work done by the external force. And work done by external force by the third bullet point is actually work done, is negative work done by the gravitational force. So with that, right, we can come out with this conclusion. So change in GPE, right, is actually negative work by gravitational force. Okay. So we are saying, right, A equals to B. B equals to minus C. A hence equals to minus C. Yeah. This is where it gets complicated already. Okay. So with that, right, you look at the equation on the left-hand side first. So U is representing GPE. So it's just a different way of denoting it. So change in U, right, is equals to minus area under FG graph. Agree? So the first equation, right, will be the same as the orange one, the line before it. With this, right, if you differentiate both sides, okay, if you differentiate both sides, you'll get something that is on the right-hand side. FG is hence equals to minus du over dr. This is not easy, okay? So this is saying, right, that suppose, right, we can have an analogy. Let me write it down. I'm just using this analogy, right, to help you see the physics in see the math, okay, through example of something that you learned before. We learned something like this before, right? Hang on. Delta P equals to integrate F dx. Sorry, dt, not dx. Okay. And we go from a earlier t to a later t. Correct? And what's the relation in the other way of writing this? F is equals to dp over dt. So you see, where did the term appear? Okay, so this math, right, if you don't understand, you can refer to something familiar and draw the relation. Okay, so that is it. Try your best to understand it. I will just introduce this first because, right, it is really important for later on, right, in gravitation, why we have certain features built into the definition. Okay, so at least, right, by then you'll be clearer. But if at this point you are not comfortable, don't worry at all. Okay, so let's go on. Finally, right, we'll go into something more pragmatic, okay, which is to talk about, right, how we apply conservation of energy, this idea, into problem solving. Because many of problems, right, regarding WEP are using conservation of energy. So fundamentally, right, conservation of energy is about accounting, okay? And accounting, right, you need to draw the boundary because, right, if you don't draw the boundary, you'll become complicated. For example, you could account, let's say a husband and wife could account for their money, right, as a couple, or they can account for their money as an individual. Yeah. The husband's money will not always be the same because sometimes, right, the wife take money away from him. Okay, yeah. But right, if you consider the wife also in as part of the system, right, then you can know that the money taken away from the husband's account appear in the wife's account. So in a way, it's still accounted. Okay. So understanding the system is very important. Yeah. First, and then right, the next line is if there's no network, right, then the energy of the system remain constant. We mentioned this just now already. And if there is network, right, then total energy will not remain constant. And what do we do? Okay, because the energy will have changed. It doesn't matter as long as you know, right, where did it go to, or where did it come from. Then you can still equate things. So let's use examples, right, to understand this. And I'll use one example and 3 ways of understanding solving the same example. And without further ado, the first way is to account in terms of gains and loss. Yeah. We know, right, that change of some certain quantity, right, is equals to final minus initial. And a change in quantity, right, can be a positive or a negative term. And that's where, right, students blur already because it's difficult to deal with negative items. But then it's easier, right, to say things in terms of gains and loss. Okay. I could have change in a quantity, change in, let's say, KE, 50 joules. Okay. Minus 50 joules. That means, right, the KE has decreased by 50 joules. But right, I could say the loss in KE is 50 joule. And in saying that, right, I will have avoided minus sign. So saying things, right, by gains and loss, right, will avoid using minus sign. Moreover, right, we can also account for what is the effect of work in the this whole picture. Okay. For example, right, if there was a work done against friction, okay, then it will mean that there will be gain in some thermal energy on the tabletop. Okay. So that gain, right, will also appear on the same side as all the terms that have the gain. Okay. And if, right, you have work done by some other forces, right, okay, that's helpful. And that term, right, will be written on the same side, right, as the losses term. Okay, because, right, it's like allowing someone else to gain, or someone else is doing work, allowing for someone else to gain. So you'll be on the opposite side of the equation as gains. So let's look at this for this example here. 15 kg box, right, initially at rest, blah, 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 pull up 30 degree incline, constant force 200 Newton, friction is 80 Newton, move up by 20 meter. Okay. So in applying the first method, right, our equation will look like this. You see this guy, right, obviously gain KE because it started from rest, right? Yeah. So there's a gain in the KE. What else is gaining? GP is gaining. Yeah. So in this example, right, there's actually no loss in some energy per se. So if there was a loss, then you write on the right-hand side of the equation. Then you have a work done against friction. I say this is like a sort of a gain in the thermal energy. Okay. Right-hand side, you have work done by pulling force. So 4 items. Next step, I substitute in the terms partially. I didn't substitute in the mass, but that's fine. Okay. So you can see how the terms lay out, and all terms are positive terms. Okay, all terms are positive terms. Even the work, yeah, you see, it's a work done against friction, right? Friction act down the slope, displacement is up the slope. How come this work is a positive quantity? Because, right, I didn't call it work done by friction. I call it work done against friction. Okay. Therefore, right, work done against friction, that will do the trick, right, in making the negative sign disappear. Yeah, because I already say it's a work against friction. So since I accounted for what kind of work it is, it will just be a positive term. Okay, now the second way of writing the statement. So the second way of writing a statement will be something like this. Okay, you will talk in terms of network and its effect on the PE and KE. So you will have both things appearing. Okay, both KE and PE. This is in contrast with the third form, which is only KE. We'll talk about that in a while. When do you use this? You use it when potential energy is involved. Yeah. So the same problem, the same problem, we can solve it, but now it looks a bit different. Okay. Here, change in KE. Change means it must be a final minus initial. Okay. So final is half mv squared. Initial is 0. So it appears in this order, not because of other reason, but because it happens to be so. Half mv squared is the final, 0 is the initial. Yeah. Whereas when you deal with the increase in KE, the two terms appear in the same order, but they mean different things. When you say that something is an increase, you are simply taking the bigger one minus the smaller one, or not final minus initial. It's big minus small when you say it's an increase. When you say it's a change, then it will be final minus initial. Change in GPE, here mg, you also take the final height minus the initial height. Okay, so here 20 sine 30 minus 0. Now you see, all the work will be on the right hand side of the equation by this formulation. So you will have all of them are work done by already. No more versus. Okay, all work done by. So here you have the 80 times minus 20, appropriately so. Okay. Then the last term, 200 times 20, no change. Lastly, third formulation, sometimes we call it work energy theorem. It is sort of like treating, we only believe KE as the pure real energy, or all other energies, are simply work, okay, including, potential energy. Because, we can actually relate, potential energy with the work done by that particular force. Because every bank, have their corresponding banker. Yeah. So when we want to say, the change in potential energy, we can turn it into, a work done by the relevant force. Okay. And so, in this question, in this formulation, there's no more PE. All the PE, will appear in the equation as work. So left hand side, change in KE, only thing. Right hand side, all the work. There are three forces here. They are doing work. Normal contact force does no work. Okay. So you see that, work done by weight appears as mg times minus 20 sine 30 degree. Yeah. Because mg is downwards, the displacement is generally up the slope, upwards. Yeah. So these three ways, you'll see that the math work out to be identical. Okay. It's just that the initial placement of terms, will be different. I hope you can see the four terms, are identical. They just appear at different part of the equation. Okay. So this will be one of the very useful thing, for you, because you will decide what is comfortable for you to use and just stick to it. But I will suggest, you must at least know two ways, because sometimes you may be limited if you only know one. Yeah. So with that, that concludes today's review. Okay. And I hope you can follow up, by going to try some problems. Yeah. But if not, at least, I would think that if you can understand the meaning of potential energy, get your understanding of work and the relation between work and potential energy, right, clear, that will be a good foundation to move into gravitation. Yeah. So that's all, and thank you.